Okay, today we're going to be looking at another part of our Year 13 integration, something called integration by parts. Actually, possibly one of the more straightforward bits of the integration chapter in Year 13, because quite often they'll say use integration by parts to answer the question. Where it comes from, it's the result of undoing product rule differentiation. So if we consider differentiating a product u times v, we end up with vu dash plus uv dash. Now if I integrate every term of that, the left hand side becomes uv and the right hand side becomes the integral of vu dash dx plus the integral of uv dash dx. Now what I can do with this here is make one of these two terms the subject, say let's integral uv dash dx, and move the other term across, and it's like that. Sometimes it'll be written as u dv by dx and so on in full. It might be how it's written in the formula book. But let's have a look at how it's applied, how we use it, how we set up our solutions. It's applied generally when we have a product that can't be integrated any other way. So when we're looking at this integral, for example, 5x times sine x dx, there's nothing that links the 5x and the sine x at all. So it's not like I can consider, is it the result of doing a chain rule differentiation, where that's something to do with the differential of the function here. In this case it isn't. So I've got a product here. So one of these two parts of the product will be our u term, and the other one will be the v dashed. And it's important to think what I'm going to do, what I'm going to place where and why. The u term I'm going to differentiate. The v dash term I'm going to integrate. I would like to end up with the integral. I'm still going to do an integral here, but I want to reduce this integration that can't be done to an integral that can be done. As a rough rule of thumb, if you have an x or an x squared or an x cubed term, that goes in the u slot, like here. It's not always the case, as we'll see later on. The reason, because I can, when I differentiate it, the x goes down a power. In this case, it goes down to a constant. And I can integrate sine x. We looked at it previously. Differential of cos is minus sine, so the integral of sine is minus cos. And then my integration becomes, yet again I'm using I equals because I've got working in between, and I can rewrite it there. I equals uv, this times this, so minus 5x cos x, and then minus the integral of the other two parts. Notice my setup for the u dash v dash is exactly the same as for product rule, for quotient rule, and now for integration by parts. But what goes where is different than when I was differentiating. But if I put my little circles around that to tell me what I'm doing, it tells me here that I'm going to do the integral of this product here, so minus 5 cos x. So I've already got a minus in the formula, so minus times minus becomes plus. The integral of 5 cos x dx. So my integral becomes the term I had before, minus 5x cos x, and then differential of sine is cos, so the integral of cos is sine, so it's plus 5 sine x and plus c. And there's my integration. So it was an integration that couldn't be done any other way. I've reduced it to an integration that can be done, and then integrated it, and there's my answer there. Okay. Sometimes we'll see if we've got an x squared term, we might end up with this integration here still being an integration by parts that I have to do a second time. Later on in the course, if we were doing further maths, we might see ones that go around in a cycle, like say e to the 4x sine x, where the next integration would involve e to the 4x cos x, the next integration would again involve e to the 4x sine x, but I can do things with it to solve it. But that's really only if we're doing further maths. Let's have a look at another couple then. So example 2, I equals integral of 16x e to the 2x. Now, if this had been e to the x squared, that would be a straightforward undoing a chain rule differentiation, because the 16x would have been something to do with the differential of the power. So, but it's not in this case here. So as before, I'm going to do 16x as my u slot and differentiate it to get 16. I've got e to the 2x as my integrating, remember. So there, I've got to realise because I've integrated, I've got half e to the 2x. And then my integral becomes uv, that times that, 8x e to the 2x minus the integral of this times this, the integral of 8 e to the 2x dx. So 8x e to the 2x minus divide by 2, 4 e to the 2x plus c. Nice and straightforward. We've got a couple that involve lim. Our product here, as I say, a rough rule of thumb, if I've got x, x squared, x cubed, x to the 4, that generally tends to go in the u slot, so I can make it smaller. The only difference is when I've got ln x involved, because at the moment I can't integrate ln, so I can't put ln in that slot to go there. So I have to put my ln x here, because its differential is 1 over x. Which means the x to the 4 has to go in this one. So it's unusual that I'm going to integrate the x to the 4, to get x to the 5 over 5, but it does mean that what I'm left with, what I'm left with, that times that, is an easier integral to be able to be done. So let's do that times that then. So x to the 5 over 5 times ln x minus that times that, the integral of x to the 4, 1 over x times x to the 5 over 5 dx. And then minus, add 1 to the power, divide by the new power, x to the 5 over 25 and plus c. And I factorise common denominator, whatever, if I really had to, but that's my answer to that one there. So as I say, in this case, at the moment, try and put the ln in the u slot so that I can differentiate it. Our x, x squared, x cubed, x to the 4 in this case can go here, even though I'm making the power of x bigger, it means that product there is an easier integration to be done. But let's have a look at how we would integrate ln x on its own. This is unusual because all the others are to do with when I have a product. Now, I said before, I have to put ln x in that slot there, so I get 1 over x. I've got to realise that to form a product, I've got to rewrite the integration as ln x times 1, so v dash will equal 1, so its integral becomes x there, so I've got my u in that slot, my v dash in that slot there, my integral then becomes x ln x minus the integral of that times that, x times 1 over x is the integral of 1 dx, so we get x ln x minus x plus c. So in this case, if I've got to integrate ln x between 1 and e, I've got x ln x minus x between e and between 1. So I've got e ln e, and then minus e, and then minus 1 ln 1, 0, and then minus 1. So I get 1 as my answer there. Okay, so notice yet again, anything involving ln would have to go in the u slot. If it's just ln x on its own, to create a product, I write it ln x times 1 and then follow it through as before. And the last one looks like it's going to be a longer one. It's a definite integral. I've got limits involved as well. And I would think, because I've got the x squared, I might end up having to form one integration that I still need to do integration by parts on again. So let's see if I can squeeze it onto what space I've got left. I might have to go onto another board with this. So 12x squared goes in that slot there. Differentiate it, 24x. Cos 3x. To integrate, differential sign is cos, so the integral of cos is sine, and because of 3 I've got a third sine 3x. So my integral becomes, that times that, 4x squared sine 3x. Between my limits, pi over 2 and 0, and then minus, that times that, a third times 24, so I've got 8x sine 3x dx, between the limits 0 and pi over 2. So, I'm going to be doing this as a, I might do it as a separate 8x sine 3x dx. U equals 8x, u dashed equals 8, v dashed is sine 3x, v is minus a third cos 3x, and so in this case here I end up with I1 equals minus 8x over 3 cos 3x, and then plus integral of 8 over 3 cos 3x dx. I will need this extra little bit here, so I'm going to run out my example 4. So I'll get I1 minus 8x over 3 cos 3x, and the integral of cos is sine, so I've got plus 8 over 9 sine 3x, and that's going to go in between my limits with what I had before, so I will equal 4x squared sine 3x minus 8x over 3 cos 3x plus 8 over 9 sine 3x between pi over 2 and 0. So let's have a look what happens when I put pi over 2 in. Pi over 2 sine 3 pi over 2, 270 minus 1. Gosh, so I get 4 minus 4 pi squared over 4. And that's cancelled out there. Pi over 2, 3 pi over 2, 270, 0, 1 is 0, and then pi over 2, 3 pi over 2 is still minus 9, so I get minus 8 over 9. And then minus what happens when I put 0 in, 0, 0, and sine 0 is 0 there. So I end up with minus pi squared minus 8 over 9 with that mess there. So it's quite long-winded. This is a typical A-level question. Because of the x squared, I have to do it in 2 different parts. So I've got my integration by parts here to reduce it, so I've got x sine 3x. Then apply integration by parts to that. I've just realised I've made a slight error, haven't I? Made a slight error. Because of the minus there. What this should have done to my integration, if I1 is this, then it should have been plus there and minus there, which has an effect of making that plus and that plus there. Good job I checked, didn't it? So in that case there, when I had a look again, because it's that answer minus whatever I1 was, I might have made it easier on myself if I had called I put the minus in there and then the signs would have taken care of themselves. I might have avoided that mistake, but that stays there. So just be aware of the fact you've got potential minus sign errors. We all make them, some more than others, but we all make them, and we try and avoid them when we can.